Hello, I'm Professor von Schmohawk, and welcome to YU. We have discussed several operations which create new sets by combining sets in various ways. The union of sets contains all elements which are members of either set. The intersection of sets contains only elements which are members of both sets. The relative complement of A and B contains all elements which are members of B but not A. And the relative complement of B in A contains all elements which are members of A but not B. However, there is another possible combination. We can form a collection of elements which are members of A or B but not both. In other words, the union of A and B without the intersection. This forms what is called the symmetric difference of A and B. The symmetric difference operand is the Greek letter delta. We now have 5 different ways to combine two sets to create a new set. By using these operations to combine more than two sets, we can create interesting combinations. For example, when we first introduced Venn diagrams, we showed a diagram which looked like this. This diagram represents the symmetric difference of 3 intersecting sets. To see why, start by taking the symmetric difference of the first two sets A and B. This operation forms a set with an empty region in the middle, since the symmetric difference excludes intersecting regions. We then take the symmetric difference of the set we just formed with the third set, C. This second symmetric difference excludes any regions which intersect between C and the previous set. However, in the empty region of the previous set, there is nothing to intersect with set C. Therefore, any part of C which overlaps this empty region will not be excluded. Now, instead of Venn diagrams, let's do this one more time with 3 sets of numbers. Let's say that set A contains the numbers 1, 2, 3, and 4. Set B contains the numbers 3, 4, 5, and 6. And set C contains 2, 4, 6, and 7. We start by forming the symmetric difference of the first two sets A and B. Notice that sets A and B have the elements 3 and 4 in common. Therefore, 3 and 4 are the intersection of sets A and B. Since the symmetric difference of two sets includes all the elements of both sets excluding their intersection, the symmetric difference of A and B consists of all the elements of A and B except for 3 and 4. So the symmetric difference of A and B consists of 1, 2, 5, and 6. We now form the symmetric difference of this set with set C. These two sets have the numbers 2 and 6 in common, so their symmetric difference contains all the elements except for 2 and 6. The symmetric difference of sets A, B, and C therefore consists of 1, 4, 5, and 7. Now let's form the symmetric difference one last time using numbers and Venn diagrams. Once again, set A contains the numbers 1, 2, 3, and 4. Set B contains 3, 4, 5, and 6. And set C contains 2, 4, 6, and 7. We first form the symmetric difference of sets A and B. These two sets have the elements 3 and 4 in common, so their symmetric difference includes all the elements except 3 and 4. The symmetric difference of A and B therefore consists of 1, 2, 5, and 6. We now form the symmetric difference of this set with set C. These two sets have the numbers 2 and 6 in common, so their intersection is 2 and 6. The symmetric difference will therefore contain everything except 2 and 6. So the symmetric difference of sets A, B, and C consists of 1, 4, 5, and 7. Try creating some of your own combinations of sets using the operations we have studied. Venn diagrams are not only useful, but can be beautiful as well. In the next lecture, we will discuss another useful way to represent sets of numbers called interval notation.